Differential equations are equations that have derivatives. A first-order ordinary differential equation, or ODE, only uses the first derivative. It doesn't have any harder derivatives. These equations show how things change over time. They are important for understanding systems that change. We see these systems in many areas, like physics, engineering, and biology. ODEs give us a math language to describe how these systems change. First-order ODEs are the simplest kind, but they are very useful. They can model lots of different things that happen. Think of a ball rolling down a hill. Its speed changes as it rolls. A first-order ODE can show this. Think about how bacteria grow. This can also be modeled by a first-order ODE. These equations help us understand how systems act. First-order ODEs are a basic building block, a starting point for harder models. They are important for understanding how the world around us changes. They have many uses, making them a powerful tool for science. First-order ODEs are really important for making models of dynamic systems. These systems change over time. The equations show how the different parts of the system and their rates of change are related. This helps us guess what the system will do and understand how it changes over time. In physics, first-order ODEs describe how things move and explain how radioactive materials break down. In engineering, they model electrical circuits and how liquids flow. In biology, they show how populations grow and how diseases spread. Being able to model these things is super helpful. It helps us make better systems, make them work better, and see potential problems. This leads to improvements in lots of different areas, from making safer cars to making new medicines. First-order ODEs are super important. They are a powerful tool for understanding and changing the world around us. They have lots of different uses, and they continue to help us make new things and discover new things. First-order ODEs have a specific form. We can write it as dy dx equals fxy. Here, y depends on x. It's a function of x. X is the independent variable. Fxy shows how y changes based on x and y itself. A solution to a first-order ODE is a function that makes the equation true. It works for all x values in a certain range. Usually, a first-order ODE has many solutions. These solutions make a family of curves. We call this the general solution. The general solution has a constant, showing there are lots of possibilities. Each value of the constant gives a specific solution. We call these specific solutions particular solutions. They're like individual paths within the family of solutions. Finding the general solution is important. It shows us how the system behaves. It shows all the possible paths the system can take. An initial value problem, or IVP, adds a rule. It shows us where the solution begins, like knowing where a ball starts rolling down a hill. The IVP has the ODE and a starting condition. This condition is usually written as y(x0) equals y0. The starting condition tells us the value of y at a specific x, giving us one solution. It picks one specific curve from all the possible solutions. Solving an IVP means finding this one solution, showing the exact path of the system. The starting condition gives us important information, putting the solution in a real-world situation. It helps us model real things and guess what will happen given a starting point. IVPs are very important for real-world uses. They help us change the solution for specific situations, giving a more exact description of how the system changes. They connect theory and real-world use. Section 5. Separable equations. Separable equations are a special type of first-order ODE. They have a specific form, dy-dx equals fx times gy. The key feature is the separation of variables. The function fx depends only on x. The function gy depends only on y. This structure makes them easy to solve. To solve a separable equation, we rearrange the terms. We put all the y terms on one side and all the x terms on the other. This gives us dy over gy equals f(x) dx. Now, we integrate both sides. The integration gives us an implicit solution. The implicit solution connects x and y through an equation. It might not directly tell us y as a function of x, but it still shows us how x and y are related. Sometimes, we can solve for y directly. This gives us an explicit solution. Separable equations are pretty easy to solve. They're a good starting point for learning about ODEs. We see them a lot in different applications. They're a useful tool for modeling simple dynamic systems. Section 6. Linear equations. Linear equations are another important type of first-order ODE. They look like this. dy/dx plus px times y equals qx. Here, px and qx are functions of x. The y and its derivative are linear. Because it's linear, we can solve it in a special way. The key is something called the integrating factor. This factor is a function shown as ux. It changes the left side of the equation into the derivative of a product. ug2x equals e to the power of the integral of px dx. Multiplying by ux gives duy over dx equals uqx. Now, we integrate both sides. This gives us ui equals the integral of uqx dx plus c. Divide by u to get the solution for y. Linear equations are used in many fields. They describe lots of systems in physics and engineering. The integrating factor method is a powerful way to solve them. It's a really important part of ODE theory. Section 7. Homogeneous equations. Homogeneous equations are a special type of first-order ODE. They look like this. dx equals fyx. The function f only depends on the ratio y/x. This lets us use a special trick. This trick makes the equation simpler. The trick is to substitute y with vx. Here, v is a new helper. It changes with x. This substitution changes the equation into a separable equation. We can then solve this separable equation using the method we learned before. Homogeneous equations are not as common as separable or linear equations, but they are still used sometimes. This substitution trick is a smart way to solve them. It shows how useful these tricks can be for ODEs. After solving for v, we put y and x back in for v. This gives us the answer with x and y. This whole method only works because of the homogeneous property. It lets us simplify the equation using this substitution. Section 8. Exact equations. Exact equations look like this. m of x and y dx plus n of x and y dy equals 0. There's a key rule. The partial derivative of m with respect to y must be the same as the partial derivative of n with respect to x. This rule makes sure we can find a potential function. This potential function, written as psi of x and y, has a special property. The partial derivative of ci with respect to x equals m, and the partial derivative of ci with respect to y equals n. The general solution of an exact equation is psi of x and y equals c. C can be any constant. The hard part is finding this potential function. We find it by integrating m with respect to x and n with respect to y. Then we compare the answers to find the potential function. Exact equations are a special type. They are not as common as other types of equations, but the idea of a potential function is important. It shows up in other areas of math and physics. Section 9. Substitution methods for non-standard forms. Sometimes a first-order ODE doesn't fit into any standard category. It might not be separable, linear, homogeneous, or exact. In such cases, we can use substitution methods. These methods change the equation into a form we can solve. The choice of substitution depends on how the equation is structured. There's no single way to do it. It requires some cleverness and practice. The goal is to make the equation simpler. We want to make it look like a standard type of equation. One common substitution is for Bernoulli equations. These equations look like this. d over dx plus p of x times y equals q of x times y to the power of n. Substituting v equals y to the power of 1 minus n often makes it a linear equation. Another substitution is used for Riccati equations. These equations look like this. dy over dx equals p of x times y squared plus q of x times y plus r of x. If we know a particular solution, a specific substitution can make it simpler. Section 10. Real-world applications. First-order ODEs are used in many real-world situations. They can describe lots of things in different areas of study. In physics, they describe how radioactive materials decay. They also explain Newton's law of cooling. These laws tell us how things cool down over time. In biology, they're used to show how populations grow. They can predict how populations will change. This is really important for understanding how nature works. It helps us manage resources and protect animals in danger. In engineering, first-order ODEs describe electrical circuits. They also describe mixing problems. These problems look at how much of a substance is in a mix. This is important in chemical engineering and other industrial processes. These examples show how useful first-order ODEs are. They give us tools to understand and predict things that happen in the real world. They're important for solving problems in many areas. Section 11. Further exploration and conclusion. First-order ODEs are just the beginning. They are the foundation for more advanced topics. Higher-order ODEs use higher derivatives. They model more complicated systems. Systems of ODEs describe connected, dynamic processes. Partial differential equations, or PDEs, use partial derivatives. They describe functions with many variables. They are important for modeling things in physics, engineering, and other areas. Numerical methods give us approximate solutions. They are helpful when we can't find exact solutions. These advanced topics give us more to explore. They make differential equations even more powerful. They give us tools to solve harder problems. They help us understand the world around us better. First-order ODEs are a very important first step in learning about math. They help us understand how things change over time. They give us a powerful way to look at how the universe moves and changes.